Hello everyone. Today I am going to give you the demo of the solution of the Adobe Gen AI Hackathon. So let's deep dive into the collab file. So basically this is our collab file. If we see, we have table of contents where I have written three separate codes for the isolated one, for the fragmented and for the occluded one. And I have uploaded some files which you can also upload, which was given as an input from the Adobe team. So let's get started. Let's import some necessary libraries first. These were the some necessary libraries which we need to download, and these were some necessary libraries which I've imported for our use. So basically, every content like the isolated, fragmented, and occluded one, every code is written in the form of classes. So if a person wants to use them, they can call this class, which is like this, and this class will be called and they can use their function. There are constructors and as well as very different functions in them, which I have mentioned in this overview. So if you can see the overview for every function, what function does. Like for the circles one, we are deciding first, we are detecting whether the points will form a circle or not, and then if that points form a circle, we will give the perfect center and the perfect radius. So how we are calculating the radius, we are taking the mean radius for each and every points which can form a perfect circle. Similar to rectangles, we are using the properties of the rectangles. For stars, I would like to tell that I have used an algorithm which is known as convex hull algorithm, which detects how many vertices are required to connect the exterior points of the stars, and in the star case it's generally 5 to 7. So I've used that algorithm. For line, I have used the consecutive points. The slope, if the slope of the consecutive points are between the threshold. For ellipses, it's a similar kind of thing as circles, but here we have two eccentrics, so I have used that. Then I have merged the shapes, since it can happen that if we have a broken circle, so each and every quadrant can give a circle. So if we should merge and make them one circle such that the figure looks clear. And I have updated the path. Also I have provided visualization uh, through matplotlib library, so that a user can visualize, as well as it will say whether we have how many isolated paths. So also there is a tolerance value for each and everything. So since it's a human doodle, I have set the tolerance value according to the set of inputs which we got. We can change that tolerance value and get the desired outputs also. Let's get started. Let's see the first isolated.csv file. Let's run this. So yeah, this was the code provided by Adobe team, and let's plot them. So yeah, basically this is the doodle thing. And so I have created this class. So let's run this class, and then I'm calling this class. You can see each and every code is properly formatted and properly commented for the user, as well as there is docstring for each and every function, so a user can read and understand the code easily. Let's run this file. Yeah, you can see that we get a circle, we get a rectangle, we get a star. It's similar to this one, the input file which you got, but it's properly formatted. And just we can see that there is a circle, there is a, it's mentioned that this is a circle which has a center this and radius this, rectangle and star. So also I would like to note one thing. Suppose if we pass, suppose what will happen if we pass the occluded one. So suppose if we pass the occlusion one .csv file, let's see what will happen to that file also. Suppose if it reads or not, if it's properly formatted or not for other files also. So suppose if we see this, let's just run them. You can see, you can see easily that this circle was a little distorted in this code. In this file, this circle was a little bit distorted, so it yeah, it sees whether this is a circle or not, and it's formatted this circle also. So yeah, the isolation part is quite working well, I think. Now let's get into the fragmentation part. So basically, what was the fragmentation part code? In the problem statement, we were told to find and identify the vertical, horizontal, and the radial and the other symmetries possible. So the more is the merrier, I think. So I have used an algorithm where I have created, this file is also in the form of classes. So there are functions which is a vertical symmetry detection, a horizontal, a general, and a radial symmetry detection. So vertical gives a vertical line, horizontal gives a horizontal line. General is basically a general purpose symmetry which will go through the diagonal, and there will be a threshold to that. So the slopes will vary by a bit, and this can be variable. This can be set by the user and the person who wants to do the check, like the how many symmetries can be there by the diagonal. This can be set through that, and also for the radial symmetry. So each and every function here has some thresholds. Because it's a human doodle, I have taken the input as it was given in the files, and I have used that to plot the desired figures. Let's get started. Let's see the fragmented zero code. Here you can put your own CSV path for the fragmentation one. Just change the part and run them, and it should work fine. Yeah, let's visualize them first. So basically, this was our fragmented code, and let's run. So yeah, you can see that I've created the class new symmetry finder, you can call that. And let's initialize the class. Let's run this code also. Meanwhile this code is running, let me tell you that since the vertical score and the horizontal score, and that diagonal scores and the radial scores are a bit costlier in the terms of time, since we have to see each and every point and each and every path. I have used some heuristic approach to that. I have used the middle, like in the vertical one I have used the middle, the midpoint of the whole image, and then I have seen a little bit of threshold to that, similar to the horizontal, similar to the radial, and similar to the radial score. So a bit of heuristic I have used that, because else I can, if we use the proper brute force method of checking each and every path, then it will be a quite costlier method, and this cannot be afforded for a system. So I have used a bit of heuristic approach in this, and I think even though using a bit heuristic approach, this gives a desired output. It gives around 1 minute 10 seconds it requires to take the symmetry. I think this can be taken into the account, and this algorithm may be improved, but I think this is the best which I can get through this period of time. So yeah, you can see that we are getting the vertical symmetries and the vertical line of symmetries, also the symmetry line, the symmetry score in this, the 0.34, also the radial symmetry, like this point is a radial symmetry. So yeah, I have worked on this. After that, let's get into the occlusion part, which was the most typical and the most difficult part, I think. For the connected occlusion, I have also devised the mathematical algorithm. So let's get started. For the connected occlusion, since we were said that the paths will be connected, though it will seem to us like it's occluded. So let's first create the figure so that we can understand. Uh, yeah, this was the figure, and essentially this is the first part, and this is like this. The first part goes through this way. Also the second part, because it merges with this, so we see a green colored line. If we plot separately, this will be a path of the first, and this will be the second part. So I have created, this is also in the form of the classes. And what I have done is I have taken these edges of the common points in this, and I've joined them according to the radius of the every three consecutive parts. So I got every three uh, radius of each and every 3 points, consecutive 3 points, and their radius, and the mean radius I've connected it through them. So it's quite smooth. Let me just show you the solution to that. Yeah, so you can see this is quite smooth. This is connecting like this way. It's quite a smooth and progressive way to do that. And for the disconnected occlusion one, I don't think so it was possible through mathematical algorithm. So our team has used the ResNet 50 model for feature extraction, and basically we have defined a set of images which was given as an input, and through that set of images we were through the ResNet 50 model, pre-trained ResNet 50 model, we have extracted the features of each and every images, and then we calculate the distances of each and every images with our input image. So whichever image is the nearest one, we get that and we save that into the CSV file. Also, I would like to mention that we get the occlusion one modified CSV as it was given in the question to get the CSV file. we get the occlusion 1 modified CSV file as the output here, so a person can download and see. Let's get into the disconnected occlusion one. Similar to that, let me just run this file occlusion2.csv. So yeah, basically this is the Google Drive file where I've uploaded the images of dataset. So it downloads the zip and it unzips into the this folder only, the content folder. Let's run this and let's load our ResNet model. So it's load our ResNet's model, and as well as it extracts feature from them. So yeah, this is the DS store because I was using macOS. So macOS stores some file of some images in the file of DS. So we need to remove that as it's not necessary .ds store value. So I removed that, and let's dive into the dataset images. The images are stored into this file, dataset images, as you can see. Currently I have used 10 images as it was given in the boot. I will add them more in the future. This is the images file where all features are extracted and it's checked. So yeah, we will use this feature extraction method. Basically this feature extraction function is called and it's then used. So these are some steps which have been used for feature extraction. Let's take the test.jpg file. Oh, okay, we get this test.jpg file from this plot only. So this plot.savefigure saves this test.jpg file, and once we run this it also takes these features, and then we calculate the distances and we get our desired output. So yeah, this is the way we get our desired the nearest grayscale image, which was similar to our plotted file. It was not plotted, but yeah, this was the similar image of the occlusion 2. And we can get more desired if we add more features, dataset images to this and train our ResNet model, then we can surely get more desired output, as input was limited to me, and also it was not as clear in the question, and dataset was not well provided. So I have used only this 10 images. If we add more images to that, then their features will be saved, and we can add general purpose images in this and store them and use them for our future use. Thank you. I hope so you liked my solution. So thank you Adobe and Geeks for Geeks for providing us this opportunity, and it was great, and it was great to learn from this opportunity. Thank you.